Hello, welcome to my video series of algorithms. This is part 3 of Module 1, Sorting Algorithms. In this video, we will discuss the bubble sort algorithm. Essentially, the bubble sort algorithm can be derived from the algorithm that verifies whether a list of elements is sorted. The bubble sort algorithm shares a similar time complexity with the insertion sort algorithm. Both of them run in O(n)² in the worst case and O(n) in the best case. By the best case, we mean that when the algorithms are given a list of sorted elements as input. Recall the process that we use to verify whether a list of elements is sorted in ascending order. We compare the ith element with the I plus 1th element and repeat the process for each index I. We claim the ith and the I plus 1th elements are sorted if the ith element is smaller than or equal to the I plus 1th element. If we have verified the property for all indexes, we can claim that the entire list is sorted. Note that such a verification process takes O(n) time. If we are given an arbitrary list of elements that may not be sorted, we may find some cases where the ith element is larger than the I plus 1th element. For these cases, we can swap the ith and the I plus 1th elements to make the list more sorted. Consider the input list of elements of 1, 7, 3, 2, and 5. We apply the verification process to this list of elements with the auxiliary swap operation. For example, we begin by comparing the first and the second elements 1 and 7. No action is needed since they are already sorted. We proceed with comparing the second and the third elements 7 and 3. Because they are not sorted, we swap them. We then compare the third and the fourth elements 7 and 2 and swap them because they are not sorted, and so on and so forth. After the completion of the process, we can make two observations. First, we see that the largest element will be placed in the last position. This is because the largest element will always be swapped to the right and compared in the next iteration. Second, we also see that the remaining list may still appear unsorted. For example, the first 4 elements in the previous example are 1, 3, 2, and 5, which are not in sorted order. Fortunately, we can develop a sorting algorithm by iteratively finding the largest element in the current set. The idea is similar to the selection sort algorithm. That is, we will simply repeat the same procedure for the first n-1 elements, as we have already put the largest element in the last position. Let's complete sorting the previous example. We use brackets to highlight that 7 is the largest element and has already been placed in the correct position. We will repeat the procedure for the first 4 elements 1, 3, 2, and 5. In this case, we only need to swap 3 and 2. After this iteration, we have put the second largest element 5 in place. Finally, we will run the process for the third time on the first 3 elements 1, 2, and 3. The algorithm will not make any swap, which indicates that all numbers are sorted, and we can terminate the algorithm. The above algorithm resembles the scene where the bubbles are rising to the surface from deep water. Therefore, the algorithm is called bubble sort. Here is the pseudocode for the bubble sort algorithm. We use a Boolean variable t to keep track of whether swaps are needed in the current iteration. If no swap is needed, we will terminate the algorithm in line 10. Now, let's analyze the bubble sort algorithm. We claim that the algorithm is correct because it can always find the largest element and put it in place. The rest of the proof resembles that for the selection sort algorithm, which is presented in part 1 of this module. For its computational efficiency, we observe that the pseudocode contains 2 layers of for loops. Both may iterate n times in the worst case. Therefore, its time complexity is O(n) squared. Thanks to the predetermination criteria introduced in line 10 of the pseudocode, the bubble sort algorithm can recognize a sorted input list and runs in O(n) time in the best case. Finally, for space efficiency, we claim that bubble sort only swaps elements rather than making any data copy. Therefore, the algorithm requires O(n) space and is an in-place sorting algorithm. In summary, we have introduced the bubble sort algorithm in this video. It shares a lot of similarities with the insertion sort algorithm in terms of both time and space complexity. They are both in-place sorting algorithms that take O(n) squared time in the worst case and O(n) time in the best case. In the next video, we will discuss the shell sort algorithm. Thank you for watching and see you next time.